So just a brief overview of the content. So we will begin by introducing SCION Instruments to those of you who are new with us and don't know who we are. We will then proceed to discuss how we do root cause analysis and troubleshooting, and this is via a troubleshooting protocol that include diagnostics for pressure, leak, variable retention times, peak shape, and column considerations, which can really help with preventing a lot of the troubleshooting problems that we see. We'll then round off with just a very brief summary. So, who are SCION Instruments? So, SCION Instruments are a leading manufacturer of gas chromatographs, mass spectrometers, high performance or high pressure liquid chromatographs, and also the accompanying chromatography data system, which is Compass CDS. So we have two main sites. One is based in Hoos, the Netherlands, which is the manufacturing facility, and the second is the Research and Development Centre, which is Livingston in Scotland. So in 1948, Varian was founded in the USA, and this continued until 1998, where it expanded and Chrompac was acquired by Varian. The manufacturing was then moved to the Netherlands. In 2010, the GC and GCMS product lines became part of Bruker, who then moved into TechComp, then acquired the GC, GCMS and CDS product line. We do state-of-the-art manufacturing facility open in Hoos, and we also launched our LC6000, the Hplc. So we are a team of dedicated and experienced technical and support staff for the whole global market, and this is for sales, applications, custom solutions, and service. We are committed to continuing the 50-year legacy of our product and service through a dedicated research and development team. Now, getting into the reason why we're all here, and that is looking at how we troubleshoot and do root cause analysis for Hplc. So to do this, we must use a troubleshooting protocol. So there are many different potential sources of chromatographic problems associated with Hplc, and there can be overwhelming work. A troubleshooting protocol will streamline the process of not only identifying and fixing the problem, but also preventing the issue from occurring again, or at least reducing the likelihood of the issue occurring. So there are 5 main steps that we need to undertake when writing the troubleshooting protocol and following it through. So the first of the step is identifying if there's a single problem, if it's multiple problems, and what actually is the problem. So this is usually done by observing a change in chromatography or observing a change in system performance. And obviously, if it's an issue, then we're going to have decline in system performance. So once we've identified what the actual issue is, the next we need to source where that issue is coming from. To do this, we need to do a step-by-step walkthrough of the Hplc, making sure that we only test one module at a time, so we can fine-tune where the issue is and get it fixed. Once we've sourced the issue, we then need to fix them. To begin this, we need to ask why has the issue occurred. We want to have an immediate fix of the issue. We also want to prevent it from happening. Once we have made any modifications to the instrument or the method to get the better chromatogram, we then want to test the instrument to ensure that performance has been re-established. The fourth part of the troubleshooting protocol is taking preventative measures and having proactive handling of the instrument. This includes routine maintenance and taking care during column selection, which we will talk about. The final process of the protocol is making sure we have documented the whole process. So having clear, concise, and detailed records will allow us to look back upon the issues that we've seen if we do see future issues. So before starting any troubleshooting on the system or looking at a chromatogram, it's important to understand where the issues may be coming from. So we only have three choices for HPLC. It's the hardware, the mobile phase, or the column. All three can cause their own issues, but they can also have an escalating effect on the analysis and the chromatogram obtained. So the main issues that arise are from the mobile phase, the pump, the injector or the injection, the column, the detector, and for tubing and connectors. Using that dedicated protocol will help us to isolate the main cause of the issue and help us change the way we work and the way we treat the instrument, which will help prevent the same issue from happening again. So once we have looked, the next part is actually starting to identify the issue. So it's always good practice that when a new method is to be performed on the instrument for the first time, that we document all the method details, including sample preparation, the age of the column, and the mobile phase preparation, including details such as the balance that was used in the pipette, will really help in troubleshooting future issues. By monitoring the pressure of a HPLC each time a new column is used or a new method is used on that column will also give us a great baseline idea of what the system performance is at the time of setup. Doing that will allow us to monitor the frequency that the issues occur and also if there's a recurring theme. So it's also good practice to perform in-house column validation using the reference standard used within the column. This will be provided on the column datasheet. Once we've verified that the column is up to specification, we then need to run a reference standard for the target analytes. Keep a laboratory record of all the tests run on the instrument, including the number of samples analysed, the total analysis time, and any maintenance performed on the system. This is all going to help you troubleshoot faster in the future. Any additional information, such as QCs that have passed or failed, and any chromatography observations at the time of data analysis are also recommended. So identifying whether something is spending any time, money or resources fixing an issue that isn't actually there. So for example, when we run a gradient program, there will be a natural pressure fluctuation as the percentage of the solvent changes. So if we run a gradient method, we should observe what the natural fluctuation is. And then in future analyses, if this observation stays the same, then we know that there's an issue. If it falls outside of the natural deviation, then that is when we should be troubleshooting. Don't just presume that a small fluctuation is actually an issue. When the issue has been identified, we then must understand whether it is a long-term problem or if it's a short-term problem. Has the change happened overnight, or has it been a growing problem that has now reached unacceptable levels? Is the issue reproducible, or is it a one-off occurrence? For example, if you've got a bad injection, this doesn't always require maintenance. Repeat the test and see if the same issues are reproducible. Predefining acceptance criteria will allow us to determine when action is actually needed. So part of identifying the issue is to know whether it's been caused from the hardware, the column, or the mobile phase, all of which will result in poor chromatography. So if all peaks in the chromatogram are affected by the issue, then the most likely cause is due to hardware. However, if only individual peaks are affected, then it's more likely to be chemical, mobile phase, or column related. This will give us the starting point of moving through this troubleshooting protocol. If you do suspect it is a problem with the system, compare the latest chromatogram with one obtained at the time of the column installation and note any changes in the chromatography. It's key to remember that it's not always best to operate on just a short-term solution. Taking time to fix potentially long-term issues is just as important. So next we need to find out what the source of the problem is. We know we have the problem, we've identified what the problem is, but where is it coming from? So it's always best to start with just a simple check of the most commonly known causes. Is the flow rate set correctly? Is the pump delivering the actual flow rate that we've set? Do we have any leaks in the system? And if a gradient program is being used, is in the right mobile phase, we must do a full systematic diagnosis. Start with the obvious and then move to the more unusual cases, which usually take longer to diagnose. When performing the LC diagnosis testing, it's good practice to check that one module at a time. Testing more than one module on the instrument can often lead to misdiagnosis and unnecessary maintenance. Always document your findings at each stage of the testing, even if no abnormality is found. By doing this, you can then refer back to that maintenance log at the time and see if the problem hasn't been fixed or if it's a new issue with the system. So now we will look at the diagnostics around some of the most common issues that we do see with Hplc. So one of the most popular issues that we do see is high pressure. So pressure monitoring of the LC instrument is performed in the pump, as this is where the highest pressure is generated. Although the instrument is designed to be high pressure, seeing an increase in pressure from your normal pressure should not be ignored, even if it still falls within the limit of the pump. Excessively high pressure indicates that there's a blockage somewhere within the system. So the quickest way to identify the blockage is to actually remove the column from the flow path and fit a union connector instead. Once the column's removed, if you start your method where you witness the original high pressure and monitor the pressure, if it returns to normal, then you know that the cause of the high pressure is the column. So the end for it may be blocked and this will flow through the column instead even of being voided. Both will result in the high pressure that you see. We can clean a Hplc column if this is the source of the contamination or the blockage. So what we would do is initially we would just flush the column with a strong solvent to try and push any contaminant from the surface of the column. However, once we've reinstalled the column, if we still see the high pressure, we would then do a long backflush method. This will be given on the manufacturing instructions of the column as it depends upon the phase of the column that you're using. If normal pressure can't be restored by cleaning the column, then unfortunately we would need to replace the column. So what we also need to be mindful of is that each Hplc column does come with a maximum pressure limit. So when working with a new column, make sure that you document what that maximum pressure is. Applying a greater pressure to that will cause crushing of the mobile phase, resulting in overall high pressure of the system. It is good practice to set the maximum pressure limit of the LC to below that of the column. That will ensure that if your column does start, if the Hplc does start to experience high pressure, it will not damage the column. If the presence of the high pressure still remains once the column is excluded, then what we would have to do is disconnect one fitting at a time, starting from the autosampler or manual injector and work your way to the pump until the location of the blockage is identified. If we can't find any obvious blockages to the tubing, what we would need to do is purge the system in case there's any air bubbles that have trapped through as the mobile phase has travelled. To avoid this in the first instance, we must always degas the mobile phase prior to use. If we have gone through the full system and we can't actively identify any blockages, then we would recommend replacing the mobile phase filters, the flow path filters, and all tubing connecting the modules. So if we witness low or varying pressure, We would also have to do a systematic check of each module, working one at a time, starting at the detector and down to the pump. So the most common, some leaks are not always obvious. So what we'd recommend is using some blue tissue at the different connection points, specifically at the column. And obviously if it changes color, this is giving you an indication that it is leaking. An obvious but often overlooked cause of low pressure is having a low volume of mobile phase sitting in the solvent bottle. If the mobile phase isn't enough to fully saturate the filter, then we would get inconsistent or no flow to the system. If a guard column has recently been changed, the cartridge holder for that column might also need replacing. The holder is a standard consumable and contains seals. They often forgot about and are susceptible to leaking. Replacing the inlet filter in the mobile phase line is just a general part of Hplc maintenance, but again, it's often overlooked. A blocked in salary resulting in varying pressure. So the viscosity of the mobile phase is a major contributing factor to unstable back pressure. So by using a column oven, this can actually reduce the viscosity of the solvents that are being delivered, allowing a much lower and stable pressure throughout the whole system. If there is no external leaks that are obvious and purging does not help the system, then we would visually have to check the check valves and the piston seal for any damage or degradation. If the check valves are sticking, then the pressure could vary. What we always recommend is that if you're using a buffered mobile phase, that you install the plunger wash, as this would keep the seals lubricating, eliminating the possibility of any pressure variations. That's because any mobile phase that contains a high buffer concentration can precipitate out into the pump, causing blockages and restricting movement within the piston. As I said earlier, remember that the gradient profiles will give naturally varying pressure, and it's using what you know is normal pressure. Use this as a guideline, and any deviations from that, then only do maintenance then. So one of the more frustrating issues we see is variable retention times. So when varying retention time is observed, we need to determine whether the cause is due to system issues or column and chromatography issues. So to identify this, we need to measure the column dead time, or the T0. So the T0 is the time it takes for an unretained peak to pass through the column. If the T0 is variable from injection, means the retention time is being shifted due to the system itself. If it is variable, check the flow rate and that the pressure is stable. You would need to replace the check valves and the piston seals. Thoroughly degas the mobile phase and purge the system to remove any trapped air bubbles. We can also replace the inlet filter to ensure that there's sufficient delivery of mobile phase. It is good practice that at the end of each week, the mobile phase lines are primed. So flush the lines with water, IPA, water, and then fresh mobile phase ready for the next injections. If the T0 is stable from injection to injection, then the change in retention time is caused either by the method or, more precisely, the combination of the column and the mobile phase that you're using. If you are using a gradient method, check that the pump is delivering the required solvent proportion, as a slight change in solvent composition can have dramatic effects on the retention time stability. Even if you are running isocratic, but especially if you're running pre-mixed solvents or buffered solutions, prepare fresh mobile phase and inject a new sample and look at the retention times over a couple of runs. What we must make sure with any mobile phase preparation is that the pH of the mobile phase is accurate, as this does have a big effect on retention time. It's always recommended that we have detailed SOPs for mobile phase preparation, as it can help to keep the retention time and pressure stable. Different preparation techniques, even for mobile phase, can cause differences. Manual mobile phase preparation by using a low pressure gradient unit. This will deliver and mix each mobile phase individually for us, eliminating any potential human error. Low boiling mobile phases should also be made fresh and not stored for long periods of time. This ensures that any highly volatile solvents are not lost, especially in pre-mixed mobile phases. Using the same pre-mixed mobile phase for 2 or 3 days can lead to significant compositional changes compared to when it was made fresh on day 1. Monitoring the pressure map will show any abnormal changes in pressure caused by a change in the mobile phase composition throughout a run, especially for gradient. As well as preparing mobile phase fresh, if you are going to use it for a couple of days, make sure to check that it hasn't altered. pH of the mobile phase must always be in the range of the column. Generally, the pH will be 2 pH units away from the pK of the analyte. If you're using a gradient analysis, always be sure to check the column equilibration time, making sure that we are delivering the correct mobile phase composition to the column and it's not being lost in the system. If you are using a column oven, then please make sure that you check the column oven temperature. Is the actual measured temperature the same as what you've set? A small change in temperature can have a large effect on retention time, especially for viscosity that we discussed earlier. Fluctuating laboratory temperature, this must also be taken into consideration. So it must be kept regulated, especially in countries where the seasonal weather is dramatically different from each other. A method you run in winter may not give the same retention times that you run in summer if there is no room temperature regulation. Column aging, this is also a sign. This also gives the same issue of variable retention time. So when we are looking at this, we need to check how old the column is. Has it been stored for a long time? And what mobile that would be in the column? And if this is built up, then the performance of it will be affected. So we can have a loss of stationary phase on the column that will cause a varying retention time. So to protect that, we must ensure that the mobile phase is within the pH limits of the column. Another cause is mass overloading. So when we mass overload a compound onto the column, we will actually see a reduction in retention time. So what we would need to do is reduce the amount of sample that is loaded onto the column by lowering your injection volume. So now if we look at peak shapes, so this is the chromatography side where we will see the chromatography being affected. So peak shape is the best indicator for the chromatographic performance. Is that efficiency or the theoretical plate number. And the second is column asymmetry, and that is the asymmetry factor. Ideally, the AS will be at 1, which is a normal Gaussian peak. However, if it's less than 1, then it's an indicator that the peak is fronting, and greater than 1, the peak is tailing. So as with the varying retention time, the change in peak shape could be due to system performance, the method, or the column itself. Compare the latest chromatogram with the very first chromatogram from the same method. If it is the first time using the method and the column together, then it could be a combination of both the system and the method, and further investigation will be needed. If the peaks are tailing and they're also broad, then the method is not optimized for that separation, and we would need some method development. If you find that the peak shape was normal, and as you increase the number of injections, the peak shape does broaden, then this is a sign that the column has actually been degraded and is not as efficiently separating compounds. So to differentiate between the column and the system, what we would do is we would test the same Hplc using another column. If the peak shape is still the same, then we know that the issue has to be the system. We then would test the same column but on a different Hplc using exactly the same method and mobile phase. If the result is the same, then it's got to be because of the column. If both systems and all columns give the same results with the peak shape, then it's the actual method and the mobile phase that is the issue. We will also see peak broadening when the efficiency of the sample injection is not good enough. And usually what happens is we have chosen the wrong sample dilution solvent. It's not suitable for the analysis that we're doing compared to the mobile phase we're using. So to rectify that, prepare a fresh sample in either pure mobile phase or 50% organic and 50% water. If your chromatography is from the vintage, then you can look at the data rate of the detector, as this can cause peak broadening. Make sure to set the data and the acquisition rate to the maximum value to minimize this. What we need to do is collect the most data points across the peak, and that will ensure that the peak is not subjected to peak broadening. Realistically, we want a minimum of 10 data points across the peak. By increasing the data rate, this often leads to narrower peaks, but overall increased sensitivity. This is due to the increased number of theoretical plates. The detection limit will also be greater, as we will improve the signal-to-noise ratio. So if we have a look at how the column and chromatography together and the peak shape are affected due to issues. So what you will usually see is that any peak shape change is a combination of column degradation, and it's also down to the mobile phase choice. So as we discussed earlier, the pH of the mobile phase to make the later eluting peaks more narrow. What we need to be mindful of is that it is a fine balance when using a gradient mobile phase. Having too much of a strong solvent in the gradient can actually lead to peak broadening of the early eluting compounds. So what we need to do is start off with a lower concentration and increase as the runtime increases. This is known as gradient focusing. Again, check your temperature of the column oven, as a small change can actually improve peak shape. So what we would do is a set of sample suitability tests based upon the column oven. So it's the same concentration of compound as standard, and set it at 3 different temperatures. So we could do 25, 30, and 35 degrees and see if this improves peak shape. If the change in peak shape has got progressively worse over time, then what we'd have to do is backflush the column to try and remove any of the contamination. If the peak shape doesn't change, then try replacing the guard column and the holder before actually changing the column. Peak shape can also be affected due to overloading of the column or time shift. The injection volume to minimize the change in peak shape. When selecting the column for the analysis, take specific care of the loading capacity, as exceeding this value will cause peak tailing and excessive broadening of the target compounds. Peak fronting is also caused by the injection solvent being too strong for the early eluting compounds. So we need to reduce the solvent strength to either match the mobile phase or use 100% water if the target compounds are soluble. If we notice that peaks are actually fronting, but it's a flat top peak, then we've saturated the detector. We would have to dilute the sample and inject less sample after, of course, clearing the contamination from the detector. Peak tailing specifically. So if all peaks are tailing, then it's usually down to either the method, the column, or the system. We would need to investigate that further. If only 1 or 2 peaks within the chromatogram are tailing, then it is because of the method and it needs optimizing. If peak tailing is observed from the very first injection, then we can either put this to the method or the system itself. It usually is the method, and unoptimized methods can lead to prolonged interactions between the stationary phase of the column and the sample itself. If tailing is caused by the system, this is usually due to an unoptimized flow path, so we must check all connections and look for any signs of leaks. If you notice that the peak tailing becomes more prevalent over time, then this is due to the column. The column is susceptible to natural aging. Like anything in chromatography, it's a consumable and it does not have an infinite life. However, it could be contamination of the stationary phase, and this will result in poor interactions between your target compounds and the stationary phase. If you do think it is contamination, again, backflush the column and replace the guard column and holder. If your initial analysis of the sample shows the perfect peak shape and no tailing, make sure to document the asymmetry factor and use this as a reference point for future injections. This will tell you if there's a natural decline in the peak shape or if it is just a sharp, sudden change. What we do see a lot of is peak tailing due to secondary interactions, and this is known as chemical tailing. So what we want to do is we want to stop any additional interactions of your target compound with the silanol groups that are on the backbone of the column. To do this, we can use a buffered mobile phase, or we can make sure that the column we use is a high purity silica with end caps. So this will reduce the amount of exposed silanol groups on the column, meaning that the target analytes will have less chance of these secondary interactions, which will give an overall better peak shape. So one of the things we've discussed is obviously the pH of the mobile phase, and this is critical for peak tailing. So a lower pH mobile phase will reduce the ionization of the silanol groups, whereas a high pH will neutralize any basic compounds. But before changing the composition of the mobile phase, we need to check the compatibility with the column. We don't want to change the mobile phase and cause further damage. What we can also do is use a mobile phase additive. And what this will do is it will be a competing base that will interact with the silanol groups on the column, allowing the target compounds to have a better interaction with the stationary phase. Again, all we're trying to do is remove any unwanted interactions and let your target compound interact with the stationary phase. So we can actually cause degradation of the column, and this is by the high pH, too extreme of a temperature applied to it, and high buffer concentrations. All of these things will lead to peak tailing. So if we look at split peaks, so split peaks are rarely system related. They're usually column or method. So a blocked frit or column degradation is a common cause of split peaks. And if this is the reason for the split peak, it will be observed over numerous injections. As what will happen is the interaction between your target analyte and your stationary phase will become less efficient over time. So what you will also notice, if it is column blocking, the pressure of the system will also be higher than normal. and this is due to the disruption of flow of mobile phase through the column. To prevent column blocking, we always recommend that the sample and the mobile phases are filtered before being used with any HPLC. This will stop the particulates from blocking the head of column and causing any flow rate disruption. Coelution of two or more peaks can also look like it is a split peak. Obviously, if you are running reference standards, you will know what the target retention time of those compounds are. If you do see two peaks very close together, then it is usually a result of poor mobile phase selection, or it needs a gradient program to be run so we can increase the amount of organic in the sample or reduce the amount of organic sample to separate those compounds out. When the injection solvent is stronger than the starting point of the mobile phase program, especially in a gradient method, reproducibility will be an issue and we will see more peaked splitting. So if this injection solvent is too strong, it won't just affect peak shape, but it will also affect sensitivity. So choosing the right solvent selection for sample dilution is a key part of method development. Again, to find the best injection solvent, we can run a series of system suitability tests using the same concentration of reference standard, but have varying solvent compositions to identify what gives us the best peak shape and best peak area. So what happens if we actually have no peaks? So if a chromatogram shows there's no peaks and there's no baseline noise, then this means the signal's not actually either reaching the detector or leaving the detector and entering the data system. If there's no visible peaks, then we must check that the lamp is turned on. And if it is coming on, then we must run a wavelength check and also a lamp energy check to check that the lamp's not defective. If the connection between the detector and the data system is okay and the lamp is turned on and operational, then the next thing we would do is check the flow path of the detector to make sure that the flow cell is not blocked by an air bubble. We can flush the flow cell to remove any air and also any impurities. If the chromatogram shows a baseline but no peak, check that the optimum wavelength is selected for UV-based detectors or the target refractive indice is between the specified range of an RI detector. We can check that the mobile phase is flowing freely to the detector. We can remove the column and use a restriction loop. Inject a reference standard, and if we can see the peaks visible when using the delay loop, this means we need to clean or even replace the column. If we don't see a peak using the restriction loop, we would then have to check the delivery of solvent through the flow path of the LC, as the sample is not reaching the column or the detector. If we've checked all of those and they are okay, the next thing to do would be check the sample vial. Is there enough sample in the vial? Check the syringe and injector flow path in case it's actually the injector that's malfunctioning. Always use a freshly prepared standard to check the detector is collecting the data. And if the data is collecting after we've used that, then prepare a fresh sample. Of course, there may be that there's no issue with the HPLC at all, and the concentration of your injectant standard is just too low and it is below your limit of detection, so it's being lost within the baseline. So negative peaks. So we must remember that it is typical when using an RI detector that we will see a negative peak, and this is normal. Usually we don't need to take any troubleshooting measures or do any maintenance. So that is because the RI will measure a difference between the reference cell and the sample cell, and this can lead to the negative peak. If you previously had a positive peak, which has then turned negative, then this would need investigation. And to do this, we would just purge the RI with fresh mobile phase and analyse a freshly prepared sample. This is usually enough to get our positive peak back. For UV-based detectors, a negative peak is observed at the solvent front, then that is because there's a UV difference between your mobile phase and the sample solvent. So what we'd have to do is re-inject the sample that has been prepared in the same mobile phase. We will also see negative peaks when the mobile phase has a higher UV absorbance than the target compound. If we can, we should change the target wavelength, but if that's not possible, then use a pure solvent that has little to no absorbance as the mobile phase. Ghost peaks is obviously something that we never want to have, as it is a sign of contamination in either the mobile phase, the column, or the injector. So to begin with, what we should do is change the source of your mobile phase solvents and your water. Use a strong solvent to wash the contamination through the flow path. And if you need to, you can add a buffer to the mobile phase to prevent contamination pool. Using we must liquid water that are compatible with the detector to prevent having ghost peaks. We should change filters in the solvent bottles and also the water purification system if you're using one, as this will introduce contamination to the system. The use of a needle wash in between injections can also prevent contamination or carryover. If you're already using a needle wash, then you can increase the number of needle wash strokes and also use a stronger solvent. Regularly flushing the injection port with strong solvent will also prevent any injector buildup. If we are getting ghost peaks because our run time is not long enough, obviously we would see this from the first injection and the second injection. You can either extend your method or do a bit of method optimization to include a gradient method. So adding a strong solvent into the injection, flushing off the ghost peak so it does not come out on your second injection. When we do use a solvent to clean the column, we will need to make sure that we increase the stabilization time to ensure the correct mobile phase is then used to re-equilibrate the column ready for the next injection. So if we're not quite sure where the contamination is coming from, we should run a long injection with no run a long run time with no sample injection. If the impurities are accumulating on the column over that long period of time, then we'd have to change the mobile phase, as this is the likely source of the contamination. If we suspect that the contamination is actually on the column and not from the mobile phase, then run consecutive blank injections, and you should witness that the peak gets smaller from injection to injection as it is being washed off the column and out of the system. So, as we've discussed throughout this protocol so far, the majority of the chromatography and LC issues that we are facing are actually due to column or method performance. So this gives just signs of the column deterioration, what we've discussed, and it just gives you something to be mindful of as the column may be reaching the end of its natural lifetime. So as soon as we see any issues that start arising, we need to become more observant on how fast the decline is and have clear cut-off specifications for when action is actually needed. If we are in doubt, we can run a reference standard and compare this chromatogram with the original ref cut, what the differences are. The same column and method on a different LC system and compare the results. And remember, taken action is important. When choosing the mobile phase for the analysis, you need to think about the pH range and the maximum pressure limit of the column, as this will lead to a decrease in column performance. In terms of how can we prevent these issues happening with the column, it is about mobile phase selection and injection solvent selection. So when you can see the normal phase and reverse phase, this is going from weakest to strongest in terms of solvent. So when we do use the gradient profile, we must take care in what solvents we're going to be using for the manipulation, So for injection solvent, as I've said, if you really are unsure, do a few different tests with different compositions. Usually 50% water, 50% methanol is good enough to get the sensitivity and the peak shape optimized. But again, the solvent choice is only dependent upon the pH and pressure limits of the column. So throughout this, it seems that everything we've discussed is for the column. Now, is it true that the column is to blame for everything? So we can't always say it is the column's fault. A lot of the time, it is the end user that is responsible. So what we need to do is be proactive and take measures to prevent the column from degrading any faster than it's not. Always the pressure limits of the column before choosing your mobile phase selection. Using a guard column where possible and ensuring that inline filters are used for the mobile phase. And pre-filtering samples on mobile phase is critical to ensure that we don't see any of these chromatography issues due to a damaged column. Run system suitability samples on a regular basis, as this can show early warning signs of column deterioration, and it will allow us to be proactive in preventing further deterioration of the column. Always take note of how old is the column, how has the column been stored if we've not used it in a while, when was it last used, and what was the method. This is all part of good housekeeping that will keep the column in good condition. Refer back to the troubleshooting protocols and laboratory logs. How many samples have been analysed on the column before we've seen any issue? What mobile phases have been put through the column? Have other end users also experienced issues? And what measures were taken to restore the column performance? Overall, the column is only as good as the care we give it. Invest time via routine maintenance and good housekeeping, and this will ensure that the column efficiency is maintained during its natural lifetime. So if we have decided that actually the column and the mobile phase have worked in combination and I actually need to replace the column, I can't restore performance through backflush, then we need to actually decide the specifications and the cut-offs for when we will replace the column. So not only will it ensure conformity between end users, but it will put a maximum limit to how many times you want to try re-equilibrating the column. So these are the recommended cut-offs. However, you should use your own specifications based upon each method implemented in the laboratory and use your theoretical plate number and the asymmetry value from the first injection to determine how much variation you're going to allow. Some final considerations before you do decide to replace the column, as we know that Hplc columns can be very expensive to replace. It is worth doing a quick system performance check once you have done your troubleshooting and you've cleared any issues that you've had. Rerun your system's performance check. So if you have pressure fluctuations, regularly check for leaks. Is the mobile phase being delivered to the system properly? And is my column installed properly? If you've previously experienced retention time shifts, is my method actually optimized? Do I need to re-equilibrate my column once a month? And are my flow rate and gradient still accurate? For distorted peaks, obviously check your mobile phase pH on a regular basis. Try not to change your injection solvent and make sure that your column isn't becoming overloaded. For changing peak response, obviously you would see on the first injection whether you needed to increase your detection scan rate, but critically you need to check that the injection volume is still consistent, especially if you are having injection to injection variability. Always use the system suitability and check your sample integrity is still being maintained. So just to summarize, always keep your troubleshooting protocol so each end user can maintain and troubleshoot the instrument in the same way. Keeping the laboratory log will make it so much easier when troubleshooting, and it can potentially stop any issues at the time that it's occurring. Before jumping straight into troubleshooting, identify if the issue is the system, the method, or the column. Often, there could be more than one underlying issue, and until we know the actual source of it, it's going to be impossible to troubleshoot. For method or column issues, always focus on the mobile phase and the column efficiency. We want to check the pH and pressure limit of the column before selecting any mobile phase, as this will prevent degradation of the column. Always run the system suitability at the time of column installation and as a routine system check on a regular basis, as this will allow us to monitor the condition of the system and the column. Having column performance be helping saving time and saving money if we can recondition that column by being proactive and taking early preventative measures. So to go alongside this webinar today, we do have 2 different guides on our website, which I've linked, and I'll send you this. This is a Hplc troubleshooting guide and also the Hplc Good Practice Handbook that we recommend using in order to prevent regular troubleshooting. That is all I have for today. You will now be unmuted, so if we have any questions, please feel free to ask or type them in the chat box. If you don't have any questions at this time, like I said, I will share the presentation and you can email me at any time.
So you are now unmuted, or at least you can unmute yourself. I've certainly opened that facility. If you have any questions, or you can type them in the chat. No, nobody. If there are no other questions, thank you all very much indeed for your time. Ashleigh, thanks for a great presentation. And we'll see you all next time. Thanks for joining today, and I hope you found it informative.
Thank you.